Now let's see analyzing of diode circuits by using approximated model. So during diode circuits like series diode configuration, parallel diode configuration, and series parallel configuration, and also parallel series configurations. So how to analyze by using approximated. Now let's see one by one. During series diode configuration, when you during forward bias, silicon diode becomes 0.7 volt, that is VD, and germanium type VD becomes 0.3 volt. That means constant value. Approximator analyzing meter is a constant value for diode when using silicon, when using or germanium. So let's see analyzing in this example by using a silicon method. Series diode configuration. So when our circuit is forwarded, VD, our ID. So our diode is made from silicon type. So when you analyze this circuit by using KVL method, Vs minus Vd minus Vr. So to determine Vr becomes Vs minus Vd. Then Vr becomes Vs minus 0.7. We use constant value of silicon 0.7. What about the current? ID becomes equal to I. I becomes V over R. So this is during forward time. What about during reverse time? During reverse time, the diode becomes a reverse to the source. So the circuit becomes reversed to our circuit. So our VD equal to our V source and ID equal to 0 and also VR equal to 0. That is ID becomes 0, sorry. Because no voltage drop during VR because our diode open. That's reverse. Assume as a diode is open. So ID becomes 0, VR also 0. So let's see by example. Let's see by the example. Series diode configuration. Let our source 8 volt during forward. Let's see our R 2.2 kilo ohm. This is VD. Our diode is made from silicon. What about the current also? So to analyze this one, so must determine VR. So during this forward by using KVL method, Vs minus Vd minus Vr, then Vr becomes Vs minus Vd, Vr becomes 8 minus 0.7, Vr equal to 0, sorry, 7.3 volts. So the voltage in this resistor 7.3 volt. 0.3 dropped through a diode. So what about the current? The current becomes voltage drop through the resistor V over R, that is 7.3 by 2.2 kilo ohm. Then let's calculate it. 7.3 by 2.2 kilo ohm. So approximately I becomes 3.3 milliampere. So this method of analyzing is approximate model during series circuit. Let's repeat this example by using a reversed the diode. When the diode reversed, that is ideally open circuit. That are VD R. Then during reverse time, what about VR? What about VD? VD that's equal to the VS, as you know, that we can call it peak inverse voltage. So VR, that VS minus VD. But we need VD and also VD becomes VS minus VR. As in during reverse, no voltage drop through a resistor. So VD equal to Vs minus 0. That Vd equal to Vs. So no drop in the resistor, and also our current becomes equal to 0. No current through this circuit. So this is the circuit configuration during forward and during reverse. So when you give it a value, that Vd becomes 8 volt. That is the voltage through a diode. What we call it that during reverse, that is peak inverse voltage. So by approximator, we can analyze series circuits during forward time and also during reverse time. Now let's see parallel diode configurations. When you see in series diode configurations by using approximator, and also the same during diode parallel diode configurations, same as the previous one I have seen. Now let's see this example. Analyze it. Now our Vs is 10 volt. Determine I1 and determine ID1 and also determine ID2. So as you know, Vd becomes 0.7 volt. So during this parallel configuration, Vd1 equal to Vd2 equal to V out. Then VR becomes V source minus VD, because VD1 VD2 equal to that 9.3 volts. What about I1? Then I1, to determine I1, equal to V source minus VD over R. Then 10 minus 0.7 over 330 ohm. So let's calculate this one. 10 minus 0.7, 0.3, I mean 9.3, 9.3 over 330 ohm. This becomes I1 becomes approximately 28 milliampere. Then also we can also determine ID1 and ID2. When VD1 and VD2 are the same type of diode, silicon type, so ID becomes I1 over 2 because of the same value. Then ID1 equal to 28 milliampere over 2. That becomes 14 milliampere. The same also ID2. ID1 equal to ID2. Then both of them are 14 milliampere. 14 milliampere. So the total current becomes 28 milliampere. So this type of parallel diode configuration, we analyze it by using KVL method or approximated method, that is constant value of silicon. Now let's see thread parallel configuration. Let's doing this analysis thread parallel diode configuration. So determine the current I1, I2 and ID2 for the network of each 2.0. So the applied voltage is set as turn both diodes. So determine I1, I2 and ID2. So let's see analyze this circuit. To determine I1, simply I1 becomes VD2 over R1. That becomes 0.7 over 3.3 kilo. So I1 becomes 0.7 divided to 3.3 kilo ohm. This becomes 0.212 milliampere. What about I2? To determine I2, let's using KVL. So we can also determine V2. V2 through this one. So V2 becomes like, let's see, Vs minus Vd1 minus Vd2. This is V2. Then V2 becomes 20 minus 0.7 minus 0.7. This becomes 20 minus 1.4. So V2 becomes 18.6. Then I2 also becomes V2 over R2. That means 18.6 over 5.6 kilo ohm. So I2, our I2 result becomes 18.6 divided to 5.6 kilo ohm. I2 equal to 3.32 milliampere. This is I2. What about ID2? So ID2 becomes this I1 is sort of I2, this becomes also this I2. So the combination of I1 I2. So let's see, I show you VD2. Yep, I mean sorry, ID2. ID2 equal to I2 minus I1. So I2, our I2 value is 3.32 milliampere. So 3.32 milliampere minus our I1 is 0.212 milliampere. 0.212 milliampere. Then we subtract, we can get sort of this diode ID2 becomes 3.11 milliampere. Diode logic gate. Diode as used as OR gate and AND gate. That means positive logic, logic 1 means E volt or V source. Logic 0 means 0 volt. So let's see our circuit. When our output is connected with the cathode side of the diodes, that we can call it OR gate. Another side, when our output is connected in the anode side of our diode, we can call it AND gate. So let's see the table. During OR gate, when V1 and V2 are both of them 0, 0 volt, our output becomes 0. But when V1 becomes 0 and V2 becomes 1, we can get our output becomes high, 1. The same in the reverse. Also the same, both of them are applied a voltage, we can get high voltage. So this principle we can call it logic OR gate. So let's show you by Meltism. This is our OR gate. When V1 is 10 volt and V2 is 0 volt, we get output. That this is our output from the cathode side of the diode. But when both of them is at low, that means 0 V2, 0 V1. Let's do it. And let's try it again high. So when both of them 0, 0, no output. Look at our LED becomes deactivated, that is off state. But when one of them 10 volt, let's see V2 becomes 10 volt and V1 becomes 0 volt. Let's try it. What about our LED? Yeah, our LED becomes activated, it's turned on. That our output is high. The same when both of them is in the diode, that means V1 and V2 is applied 10 volt. 10 volt still on, that's the LED. So during this circuit, that means OR gate circuit, only V1 and V2 become 0. Look, 0, 0. So during this one, let's try it. Yeah. Our LED becomes off state, that's deactivated. So this principle we can call it OR gate, positive logic OR gate. What about during positive logic AND gate? Said our output from the AND gate side, that we can call it positive logic AND gate. So only high output we get when both V1 and V2 becomes 1 or high. Let's show you in multi-system circuit. Look our circuit. Our output is from the anode side connected. Then when one of them is 0, what about our LED? Our LED in off state, because D2 0 volt and D1 becomes 10 volts. At what time is the LED active? When both of them is high voltage. Let's try. When I give 10 volts for this one, let's run. Yes, look, our LED becomes high. When both of them is high, our LED becomes high. That's the principle of the current flow, potential difference. So this method, you can call it our diode logic gates by specification. And simply in electrical circuits, like OR gate means as a parallel. When both switches are in parallel, the lamp is on when one of the switch is closed. Indicate as represented in as a series. Only the lamp is on when both of the switches closed. So this principle of logic, what does mean OR gate or AND gate. So this is about diode logic gates. So next we see uh, diode applications, practical application like rectifier circuits, simple diode circuits, and special type of diodes, Zener circuits. Now for today is enough.